like to welcome everybody today to our program. Thank you for joining us at the East Hampton Library for this event in conjunction with the Hamptons Observatory. We're really excited about today's program. Just thank you everybody for attending. I would like just to mention that today there will be a Q&A at the end of the program and that you can find the Q&A box at the bottom of your screen on Zoom. So feel free to use that throughout or at the end. You can pop in your question right there at the bottom and they'll be answered at the end. So just please use the Q&A for any of the questions at the end. But without further ado, I would just like to introduce Terry, who will be introducing our speaker today. But thank you everyone for joining us.
Thank you. Thank you. I'm Terry Bienstock. I'm president of the Hamptons Observatory. For those of you who know us, we've been around for over 15 years, serving the east end of Long Island in capacity of providing science education for everybody. We hold monthly lectures. We're having today. We have star parties. We do planetarium shows with a portable planetarium, especially for kids. We have a whole host of programs that we have on a regular basis all year round. The Hamptons Observatory, most importantly, provides all these programs absolutely free to the public. All of our programs are free. And although they're free, doesn't mean they're free to us. So we do appreciate any donations and fundraising. You can go to our website, hamptonsobservatory.org, to contribute. But that being the case, we're really excited. I was talking to Dr. Hasinger just a little while ago about the pros and cons of COVID. The cons we all know, but the pros is that we used to have all of our events live at a library or in a community center, and those who could drive within a half hour, an hour, would come and do it live. But it also limited who we could get to come speak to people who we were either out here or could get here in a day or so. COVID caused us to move to Zoom, and that has both expanded our lecturer base. So we have people from all over the world come and speak, like Dr. Hasinger, I think coming from Spain. Is that true?
Yes, from Spain.
Madrid. And also our participants now are from all over the world. So for wherever you're from, welcome. Dr. Hasinger is the Director of Science at the European Space Agency outside of Madrid. They're doing a lot of exciting programs and ventures all over the solar system, which I'm sure he'll talk about, and then we can take some questions and answers afterwards. You know that Dr. Hasinger is truly an astrophysicist. When I asked him what his hobbies were, and I was hoping he was going to say tennis or golf, he said black holes. And so that's amazing. So with that, Doctor, the floor is yours.
Thank you very much, Terry. It's a great pleasure to be with you. Let me just try to share my screen if that is working. Do you see the slides? Thank you very much. So it's a great pleasure to be with you, despite in 2 dimensions only, not in 3 dimensions. Today is a very special day. As you know, it's the summer solstice, or close to the summer solstice. And actually, almost exactly 3 months ago at the equinox, at the spring equinox, I gave a similar presentation to the National Academy of Sciences in Washington. And that is where actually your colleague has picked this up and has asked me to come and give this talk at Hampton Observatory. So I'm very happy to do that. I will mainly talk about the European Space Agency science program. The European Space Agency, similar to NASA, is much bigger. It also has Earth observation, telecommunications, and so on, human and robotic exploration, astronauts. So the science program is actually a relatively small part of the agency, but for me, it's the most important and most exciting part, as you can imagine. So let me start with showing you the fleet of our missions and the various incarnations of our missions. There are actually 2 slides here. One is for the solar system, and the other one is, as you will see, the so-called cosmic observers, Those are the ones that are looking outside. But here in the solar system, you have all of the planets. You have the Sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. You don't see Pluto, but you know Pluto is also part of the solar system and has been visited. And what you have here in these 3 rows is basically on the bottom, all the missions that have already happened, where we are in the legacy phase. We are still analyzing the data. And there are some exciting things like Rosetta that has landed on the comet for the first time, or Cassini-Huygens, where we landed on Titan in cooperation with NASA on the Cassini mission. And then here in the middle row, you have basically all the missions which are currently in orbit and working. And some of them have really, just been launched recently, Solar Orbiter, for instance, and Bepi Colombo. Bepi Colombo is on its way to Mercury and actually will fly by Mercury in 2 days for a second time. So we will get a close-up glimpse of Mercury. And I will talk about Solar Orbiter as well. And then here in the top row, we have the missions which are currently being built, in particular JUICE. I will talk about that in a minute, going to the Jupiter system, but then also Envision going to Venus, and then also SMILE Comet Interceptor. I will talk about some of these as well. Now, what you also see is that most of our missions are done in international cooperation. And you see the NASA flag very often. So our NASA is clearly our most reliable and longest partner. We are also doing a lot with JAXA. JAXA is the Japanese space agency. And so they are coming in quite strong, for instance, in the small planetary bodies like a comet or like the Martian moon, where we want to do a sample return mission from Mars. And then we have Russia as a collaborator. And this, as you know, because of the geopolitical crisis and the war in Ukraine, is currently with a very large dark cloud. Several of these missions we had to actually stop, cancel. There's the ExoMars mission that was supposed to fly to Mars at September this year. The ExoMars rover mission had to be stopped. But on the other hand, there is an ExoMars orbiter mission which is still going on because it has international participation, including Russia. And so we are continuing the work with international partners, like, for instance, the International Space Station and including Russia. Now, let me move to the cosmic observers, to the satellites that are looking outward away from the solar system. Here we have sorted them according to the rainbow color. So you have radio, microwave, infrared, optical, ultraviolet, X-rays, gamma rays, and even gravitational waves, which is becoming a very important area. And again, here we have the legacy missions. So there are things, for instance, like Herschel or Planck, which have worked only for a quite short time because they are cooled in the microwave and sub-millimeter range. But there are also other missions like, for instance, Exosat, where I did my PhD thesis with, or my early work, and some of the partner missions from JAXA. Currently, we have in orbit 6 extremely powerful missions. I will talk about the James Webb Space Telescope, where we are very proud to be a junior partner with NASA. In a similar way as we are on the Hubble Space Telescope, so Webb and Hubble are clearly the lighthouses. But then Gaia, I will mention, Gaia is actually currently the mission that is producing most scientific papers of all missions in history and internationally. We have Cheops, which is a small exoplanet hunter. And we have XMM Newton, an X-ray telescope, and Integral, a gamma ray telescope. So those are our current working horses. And we are preparing quite a number of new missions. And you see the NASA flag here quite often, JAXA again, and then, but also Chinese cooperation with the Einstein probe mission. And also Integral has Russian participation. We have decided to continue Integral despite the fact that there is this is a multilateral international project. Okay. So let me now go into this graph, which we are quite proud of because you see an increasing number of publications that comes out of ESA missions. And you know, the number of publications for scientists is almost something like your market share, the value of your company. And we are very proud that there is a significant increase, a doubling every 8 years roughly of the number of papers that are coming out. We have some quite long-lived missions like SOHO, XMM Newton, Cluster, and so on. But then Herschel Planck, you know what I talked about, but then Gaia is really currently outshining everybody else. And with about 1,600 papers a year, 5 papers every day, it has actually now superseded the Hubble Space Telescope, which is the gold standard or has been the gold standard for many years. But now Gaia actually has overtaken Hubble. And indeed, there is a close synergy between the two. Gaia and Hubble are working very nicely together. And in the future, I think Gaia and James Webb will work nicely together. And one number out here on the right is that we are currently contributing 12% of the total astronomy market share. So if you take all papers about in all countries, and also not just in space, but also ground-based and theory and laboratory work, ESA is providing about 12% of the total worldwide science output. So we are a small program, but quite proud of being lighthouses in certain crucial elements. Okay, now the projects in preparation shortly. We have one very big mission which will be launched next year, and it will go to the Jupiter system. It will visit Jupiter. And you know, NASA is also going to Jupiter. NASA has in particular the Jupiter moon Europa as one of its targets. JUICE will actually fly through the Jupiter system, but will then focus on Ganymede. Ganymede is one of these ocean worlds which has an icy crust. It's covered by ice, 1,000 kilometers roughly of ice steps, and then there's a liquid ocean below, and there might well be possible early molecules that could bury life or so. So this is a very interesting mission. On the other end of the spectrum, Euclid is a cosmology hunter. It's measuring millions of galaxies, and it is in particular after dark energy and dark matter. So Euclid will also hopefully be launched next year, although there is still a dark cloud on the horizon, because Euclid was supposed to be launched on a Russian Soyuz rocket. And the Russians have pulled out of our launch site in Kourou, and we are hanging in the air currently. So we are looking for alternatives, European launcher very likely, or if necessary, also a non-European launcher for Euclid. Then we have actually a number of exoplanet missions. I come to the exoplanet science in a minute. And you know, exoplanet missions from NASA, there's Kepler and there's TESS, and Plato will actually be the next exoplanet hunter. It will carry 26 individual telescopes, and these 26 telescopes cover a large swath of the sky, and so it will in particular look at exoplanets around bright stars, and hopefully can detect something like Earth 2, the second Earth-like planet. And then Ariel is following just a few years later. Ariel is an exoplanet characterization mission. So it's not discovering new exoplanets, but it is studying in spectroscopy the atmospheres of about 1,000 exoplanets. And so if you know what the Hertzsprung-Russell diagram is in star physics, it is a combination of physical parameters that the stars follow. We hope that we can detect something like a Hertzsprung-Russell diagram of planets looking at all the exoplanet spectra. And that brings me to this fleet of exoplanet missions. One very small but beautiful and really quite successful mission is Cheops that has been launched in 2019. And it is actually a small mission led by Switzerland with strong contributions from other member states, and 50% of the project comes from ESA. And it is studying known exoplanets in great detail, and is always surprising us. And it has discovered a number of golden targets, which are actually then followed up by the James Webb Space Telescope. And James Webb, being this huge observatory, will spend quite a number of hours on exoplanets. So it is indeed an exoplanet mission as well. Then there's a new kid on the block because Gaia has just discovered its first exoplanet through so-called astrometric means. Now, I didn't tell you how exoplanets are discovered, but there are two techniques. One of them is the so-called transit method, when you see the planet moving in front of the star, like a beauty dot, and you see a little hole in the light curve. And the other one is the so-called Doppler wobble technique, where you are measuring the speed of the planet, like the police is measuring your speed with a radar pistol. And so these two are the most powerful exoplanet techniques. But now we have a third one, namely with Gaia, we can really see the star wobble around the sky when the planet is pulling at it. And Gaia so far has only detected a handful of these astrometric exoplanets. But when the Gaia mission is finished and when all the data is analyzed in about 10 years from now, we are expecting about 10,000 astrometric exoplanets. So the total catalog of exoplanets will probably be dominated in the end by Gaia. Plato, as I already mentioned, is then trying to discover new exoplanets, about 4,000 to 5,000 new ones, and hopefully a handful or two handful of these. The holy grail in this kind of science is to try to find an Earth around another sun, which may carry life, and so where we may be able in 200, 300, 500 years to fly there and visit our brethren. And then finally, Ariel is, as I said before, measuring the spectra of stars, distributing the light of the spectra of exoplanets, distributing the light of the exoplanets in the rainbow colors, and then measuring the fingerprints of chemical elements in these exoplanet atmospheres. So as you see, ESA, I mean, together with NASA, but I think with an increasing fraction of discovery space in the next 10 years or so, will really start to become quite powerful in the exoplanet world. And so this is clearly one of our strongholds for the future. Now let me come to Gaia for a minute, because as I said, Gaia is really our hero. And I will just show you one discovery from Gaia, just to give you a glimpse of what fascinating different facets of astronomy Gaia is really tackling. And this is actually connected to the so-called local bubble. The local bubble is a hot bubble of gas in which the sun is embedded. The sun is sitting in the middle of about 1 million degree hot gas. And you can actually see this hot gas when you are looking in the radio. This is the whole sky map in the radio, and you see this so-called North Polar Spur or Loop 1, which is likely one part of the local bubble. And in the X-rays, when you see this beautiful E Rosita all-sky image, and it was also already seen with ROSAT, where I also worked on, you see the same hot gas bubble. And this hot gas that the sun is sitting in is quite easily seen in the X-rays. And so it was always a mystery where that hot gas comes from and why the sun is in the middle of this bubble, what the connections are. And Gaia, with its power to basically look at how the stars are moving and where they come from, where they go to, was actually able to solve this local bubble mystery. And what Gaia found out was that 14 billion years ago, there was one or maybe a small number of supernova explosions, which happened exactly where the sun is today. But the sun was not there. The sun was somewhere else at that time. And so this little movie shows you how the supernova explosion happens, how the sun is slowly moving inside the bubble, and today is basically in the center of the bubble. And while the supernova gas is pushed out, it is something like a snowplow putting together gas. And when you have a lot of gas, then new stars are formed. And what Gaia found out is that all the famous star forming regions on our sky, all the famous constellations, like for instance, I'm a Taurus, and the Taurus constellation and many others, Ophiuchus and Sculptors and so on, they were all formed by this blown out gas from the supernova explosion. So there's no star formation at all happening where the sun is today, and all the star formation happens on the surface of the bubble. And the sun is there just by chance. It was moving into this bubble a few million years ago, and now it is in there. So just to give you one detailed detective story, so to speak, how Gaia is really revolutionizing our understanding of astronomy and of the universe, and the galaxy in particular. So Gaia has received quite high accolades. This is just a few weeks ago. The Shaw Prize has been given to two of the fathers of Gaia, Leonard Lindegren and Michael Perryman. And just also about 2 weeks ago, there was also the Kavli Prize, and that went, among others, to Connie Ertz. And Connie Ertz is the one who developed astroseismology, so this theory or the science to look at shaking stars. And that was also connected to Gaia very nicely. And just last Monday, a bit more than a week ago, we have released the third batch of Gaia data. Gaia data is always basically analyzed together. You have to analyze the whole sky in all directions, and then you are putting out a huge chunk of data. And this so-called Gaia data release 3 was publishing very detailed information about 1.8 billion stars and 940 billion individual data points of measurements. And among others, the first time we were able to publish the spectra of millions of stars. What you, for instance, see here on the lower side is in blue. This is actually the so-called metallicity. So this is how many metals, more massive elements like carbon, nitrogen, oxygen, everything that we need and love is shown here in red, while in blue it's all the stars that don't contain metal. So those are the early stars. And so you see that Gaia can actually kind of disentangle where the stars came from and what their age is and what their fate is. So it's a wonderful mission. And with this, I would now like to move on to the other, maybe even more wonderful mission, the James Webb Space Telescope, which I recently read that this can be compared to the building of the cathedrals in the Middle Ages. I mean, where basically one generation started to build the cathedral and had to have a lot of trust in the next generation to continue it, and the generation following that to finish it. And something similar is with James Webb. I mean, there was more than a whole generation of maybe 10,000 people was working on Webb. And it's actually quite interesting, you know, that James Webb cost $10 billion roughly. And somebody calculated that one of these medieval cathedrals, if you would like to rebuild it today, like the dome in Köln or others, would cost roughly $10 billion as well. So similar to the James Webb Telescope. And if you compare it, one of the big aircraft carriers costs about 13 billion. So this puts things in perspective. It is a huge project. It is powerful, but it's like a cathedral, and it's worth it. This is every dollar I believe that is invested is really worth it. I'm very happy that we, in the end, decided to put cameras on the top of the Ariane 5 rocket. That was not guaranteed because ESA usually doesn't put cameras on their rocket. Only I think the competition started to put cameras everywhere, and so we realized I think it's better to put cameras on board. And indeed, we were very lucky because the Ariane 5 launch was just perfect. It was a picture book launch. And we didn't expect what we saw. I mean, our jaws dropped open because we thought that when the rocket is going up and then there's a separation between the upper stage and the telescope, that everything would shake around a little and we wouldn't really see a picture. We would just see things moving around. But Ariane has put us out and has kissed us goodbye so smoothly that both the Space Telescope itself and the Ariane 5 upper stage were absolutely stable, and it was like a movie scene. And James Webb actually realized this very quickly, that it is already stable and that it is already facing the sun at the right direction. And so immediately started to automatically pull out the solar panels. And so we were extremely surprised that the solar panels came out, and then we were actually, they came 3 minutes too early. and that we were able to watch that was really breathtaking. And so there was an extra applause for the Ariane 5. And the Ariane 5 has actually also made something else wonderful, because it has put the telescope in such a precise orbit. There was very little fuel necessary with these correction thrusters to move it into the right orbit. And that means that there's now a lot of more fuel left to operate the telescope for a total of almost 20 years. So we were also able to increase the lifetime and therefore the amount of science that will come out of the telescope dramatically. Now, the unraveling, the unfolding of the solar panels was just the first mechanical event that happened. But then there was a whole 30 days of terror that happened, because 340 individual mechanisms had to work flawlessly. And many of them, if they would have failed, would have caused basically the death of the mission. And so you probably know the 7 minutes of terror when the Mars rovers are landing on Mars and how many different things have to happen. This is way more complex than a Mars landing, and it actually led to 30 days of terror. But finally, everything worked just like clockwork, like a Swiss clock. Everything is working, and it is really now beautiful to see that all the mirrors are folded out. They are all at their right position. I'll come back to the mirrors as well. But just a nice story in between. You know that both Gaia and the James Webb Space Telescope are in a similar region in the solar system, namely at the L2 point, the Lagrange point 2, which is moving around the sun together with the Earth. And they are not exactly at that point. They are both in long, large, about 800,000 kilometers long orbits. So the blue one is the James Webb Space Telescope, and the green one is Gaia. So each of them has their own orbits, and they never come closer to each other than about 1 million kilometers. But you know that Gaia is scanning the whole sky. And therefore, whenever the James Webb is in the field of view of Gaia, then Gaia sees a little dot for the James Webb Space Telescope. And this was used, normally Gaia doesn't transmit images, but this time it was used to make an image and to send a picture postcard from Gaia to Webb. And this was not just fun, but it was actually interesting to see that Gaia was able to determine the position of Webb among the stars to a better accuracy than Webb itself. So we found that James Webb is about 40 meters away from the position it was thinking it is. And so Gaia could actually improve the location of Webb. And we will continue to do that. So the next few years, we will get more and more data points from James Webb itself. And at some point, James Webb has promised that they would return the favor, that they would actually also look at Gaia at some point. And so we are looking forward in the future of a very nice cooperation. And now let me come back to the mirror. So the mirror itself, you know, is made out of 18 individual hexagons made of beryllium, very lightweight, but also very flimsy material. And they have to be aligned perfectly to better than a hair, or much better actually than the distance of a hair. It's about a 10,000th of a diameter of a hair that they have to be aligned. And that was done in March for the first time, and that basically ended up with this beautiful sharp image of a star. And the engineers got really very excited, because the image is actually somewhat sharper than they were estimating it to be. And so indeed the so-called diffraction limit of the telescope is now at 1 micron and not at 3 microns. So it's better than expected. Now, a few weeks ago, there was a micrometeorite that hit one of these mirrors and actually put a hole in it and a scratch, and also kind of deformed the shape of that mirror. And that has actually caused a very slight, maybe a few % change in the point spread function of James Webb. We hope that this will not be too frequent. I mean, this micrometeorite was larger than anything that was expected before. And indeed, Gaia is helping James Webb, because Gaia can measure the size distribution of micrometeorites in the position where James Webb is. And Gaia says that Webb should not expect another one of these bad guys in the next 10 years. But let's see how it goes. So just see how extremely sensitive the stuff is that we have put out there. A lot of as I said, the engineers were most excited about this very sharp picture of the star, but a lot of astronomers were more excited even about what is behind the star, namely all of these faint galaxies. And so if you exaggerate the cut of the image a bit, then you see about 400 to 500 extremely faint objects, so much fainter than anything that has been seen in this area. What you also see in the infrared, the detectors have quite some memory of if the bright star was shining on one part of the detector, there's quite a long memory of that event. And so you also see these ghost images of the same star on the detector. So infrared images are not easy to analyze, but I think they are working on the software to make it perfect. And in a few days, I believe on 12th of July, we are really expecting to see the first color pictures and the first spectra of James Webb. Now, before that, they have also analyzed and aligned all the 4 instruments on Webb. So you know that there are 4 instruments in the focal plane. One of them is NIRSpec. This is built by the European Space Agency, so that's our baby. NIRCam is built by the US, by NASA. MIRI is actually jointly built between ESA and NASA with a European principal investigator. And MIRIS has been built by the Canadian Space Agency. So each of the space agencies has provided golden real estate in the focal plane of the telescope. And you see the same sharp images everywhere. So it doesn't matter which telescope, which instrument you use, you always get the same sharpness of the image. And I would like to concentrate a bit on this MIRI image because you see that it has, unlike the other images, this is looking into the Large Magellanic Cloud, where you mainly see stars from the cloud itself. But in the MIRI image, you also see the gas, the cooler stuff in the cloud. And so this is actually a very nice blow up of the MIRI image in comparison to what Spitzer was able to see before, or even what WISE, there's the WISE All-Sky Survey, which is a very small telescope looking at all the sky. Spitzer has so far been the best telescope in the infrared, but now you see how James Webb is really outshining everything and how even individual stars here are basically splitting up into much more complex things, and how you see the gas in the background. So wonderful stuff. So we're really, our appetite is whetted to look at these kind of images in color, because you can learn a lot about the gas physics and about the stars and everything else. Now, I always say, well, a picture is worth 1,000 words, but now we have spectra, and for several of these cameras, we will have spectra in individual pixels. So you don't get just one spectrum, but you get thousands of spectra. And one spectrum is worth 1,000 pictures, I would say. So the real physics comes out of the spectra. And the very first spectrum that has been distributed from MIRI on James Webb is this blue line here. It is an active galactic nucleus, a black hole. So, one of my hobby horses with very broad emission lines, which is hot gas was swirling into the black hole. And this yellow line shows what Spitzer was able to see before, and you see how much more information there is coming out of James Webb. So we will be blown away by the amount of information, and there will be many, many careers and many PhD theses that will just kind of eat away from the beautiful James Webb data. Now, I personally am interested in the early universe, and in particular in the history of black holes. In the fate of the universe that is actually affected by black holes. And therefore, I'm looking forward to the deepest images with Webb, which are in particular sensitive to the first light in the universe. The universe is expanding, and everything that is moving away from us, but the further the objects are from us, the faster they are moving away. And moving away, it's similar to what I said before with the radar pistol of the police. When something is moving away from us and its light is shifted into the red part of the spectrum. And in the earliest universe, everything that is emitting in the visual light, like stars, is already redshifted into the mid infrared. And so therefore you need to observe the early universe in the infrared. And this is the deepest image that Hubble has ever taken. And on the right side, you see a simulated image, what is expected at a similar observing time with Hubble from Webb. And Webb is actually 100 times more sensitive than Hubble in the infrared. And so in particular, we are interested in these things which are extremely red, which are only showing up in the long wavelengths mid-infrared channels. And those might very well be, so near infrared channels, sorry. Those might very well be the earliest galaxies and stars that we can observe in the universe. And there's a big debate. I cannot go into great detail right now, but there's a debate whether the dark matter is actually produced by primordial black holes. If this is the case, then James Webb should find about 10 times more of these red little dots than there are in this simulated image. And so the very first deep images from Webb could already solve, if we are lucky, a fundamental puzzle in history of the cosmology, namely, what is the dark matter? And with this, I have to leave Webb, unfortunately, and I will now move on to Solar Orbiter, coming back home. Solar Orbiter has been launched by NASA in early 2020, just before the pandemic started. So we were really lucky that we were all able to go to Florida and see the launch on an Atlas V rocket. And what we see here in this little movie, let me show it once more, the fact that the sun is getting bigger in this movie is because Solar Orbiter is coming closer and closer to the sun. Solar Orbiter is on its way to the inner solar system. It is has reached the closest distance of about 0.3 astronomical units. And the pictures that come out of these close-up views are really spectacular. I mean, they are really spectacular. This picture here on the left is on the Webb. You can actually zoom through it. It is about a 9,000 by 9,000 pixel image, so it's completely impossible to display it on a screen. But when you zoom in, then each of these images contains still oodles of structure, and there are these very fine details. For instance, the so-called campfires. When these things are moving, you can see that they are burning like flames. There's also on the south pole of the sun, they have discovered something completely unexpected. They call this a hedgehog structure. And Solar Orbiter will actually work its way higher and higher up in the ecliptic and will actually be able to look at the pole of the sun and therefore have a unique vantage point to understand our sun better. This is a recent image that has been taken on 15th of February, where the sun had a major so-called coronal mass ejection. So that was an explosion on the surface of the sun, and this was one of the biggest things that has ever been blown out. If something like this is actually directed towards the Earth, then we can really, it's really dangerous to be out there. So astronauts, for instance, could really be damaged. They could be seriously affected in their health, and then also satellites could be destroyed, and also the power grid on the Earth could be heavily influenced. At least this has happened in the past 100 years, so it's very important to understand the sun. It's very important to understand the space weather, and Solar Orbiter will actually be a unique asset in understanding the sun better. And with this, I would now like to come to a very sexy project, which is Comet Interceptor. And we have this is our youngest mission that we have adopted. ESA, our kind of government, the Science Program Committee, has selected this mission. And this is the first one of these fast flexi missions, which are reacting to new scientific challenges relatively quickly. So 3 years ago, when we were preparing for the last ministerial meeting, we did not yet know that this mission will exist. But we already knew that there are these fascinating objects like interstellar visitors or otherwise comets that have never visited the inner solar system, and therefore they are pristine objects that stem from basically when the solar system was built. The comets, they are the rubble of the construction site of the solar system. And every once in a while, one of them is kicked into the inner solar system. And if you find one which has never visited the sun before, then you are looking at material which is basically coming out from the pre-solar nebula. And this comet interceptor is quite cute. We will launch it together with Ariel, with this exoplanet hunter, and we will park it at the L2 orbit, close to the space to the James Webb Space Telescope. So this L2 region will become quite popular. Plato will go there, Ariel will be there, and then Comet Interceptor will wait until somebody else discovers one of these new comets. And then if that comet is actually crossing the Earth's orbit at a location that the Comet Interceptor can reach, then Comet Interceptor will set in motion and will actually fly there in order to intercept that comet and to fly through the coma of that comet. It will actually release 2 sub-satellites, so it will be a mothership and 2 baby sats, and they will be able to see the comet from different angles, from different directions. Mothership will stay a bit outside, so in a safe distance of about 1,000 kilometers, but the 2 sub-satellites will go to something like 400 kilometers, which is quite dangerous. If the comet is active, then there's a lot of dust around. So this could be a suicide mission for the smaller sub-satellites. But it is a once-in-a-lifetime opportunity, and so we are really looking forward to intercept one of these comets. And that brings me now to the long-term vision, to things that happen in the next decade and beyond. First, we still have to fulfill a promise to the worldwide astronomers to build these 2 powerful flagship missions. One is called Hasinger, which is an X-ray telescope similar to Chandra and XMM Newton, but about 10 times bigger. And then the other one is this wonderful gravitational wave observatory interferometer, LISA. And what is shown here, bringing sound to the cosmic movies, and this is coming back to my hobby horse. If you have black holes, for instance, which are 2 black holes which are merging with each other, and there's a huge explosion of gravitational wave radiation, but very likely there will also be a huge explosion of light, because there's a lot of matter around, and these black holes will then swallow that matter. And so X-rays and gravitational waves together will actually be able to observe completely new facet of the universe. And then once this is finished, we can then embark on the next long-term planning cycle. And you know that National Academy of Sciences is actually doing these decadal surveys for NASA and NSF, and they do this typically every 10 years. But in the recent 2 surveys, they realized that they have to look at a much longer timescale. So they were also looking at 25-year timescales. And this is actually quite nice, because ESA has always looked at roughly 25 to 30 years timescales for their large missions. And LISA and Hasinger basically were the ones that came out of the previous priority setting. They were called L2 and L3. And now we are calling L4, L5, and L6 the next large missions. And the scientific community in Europe has made this prioritization similar to the decadal survey. And they came out with 3 very exciting topics. One is the moons of the giant planets. So this is the theme that I already talked about, where JUICE is going to the Jupiter system. But there are other moons in the solar system that have these ocean worlds underneath. This is actually an artist's concept of the Enceladus mission. Enceladus is, sorry, not the Enceladus mission, but the Enceladus moon. Enceladus is a relatively small moon, but it also has a liquid ocean underneath, and it has cracks in this ice, and so water is coming out of that ocean. And so ideally, if you fly through these plumes, or even more, if you land there, you can analyze the water that comes out, and you could look for life, signs of life there. And a dream that I come to is that maybe we can join forces with NASA, and we could do a sample return mission from the surface of Enceladus. So basically bringing cryogenic ice samples back to Earth and analyze them here in great detail. So this is an exciting perspective. And the L5 mission is also an interesting thing. It is either focusing on exoplanets or it focuses on the Milky Way in a similar way as Gaia is focusing on the Milky Way. I come back to that theme because the scientific community couldn't make up their priority independently from NASA. So they said we do either the temperate exoplanets or we do the successor of Gaia in the near infrared. And I'm coming back to that. And then the third theme is more or less following up on the exciting cosmology, where Europe also has developed the leadership both with LISA, the Gravitational Wave Observatory, and with Planck, the Cosmic Microwave Background Observatory. And so something either in gravitational wave or in cosmic microwave background will also be on the horizon for the future. Now, I already talked about decadal surveys. The one on astrophysics came out 2020, and it was actually interesting to see that NASA has made priorities which are kind of commensurate or orthogonal to the ESA authorities priorities. But NASA has basically defined that their highest priority flagship mission will be focusing on temperate exoplanets. So it will hopefully do an image and a spectrum of an Earth-like planet and look for signs of life. And this is pretty similar to our central theme here. And the fact that National Academy and NASA have selected this as the highest priority means that we will not select it as our L-class mission, but we will try to collaborate with NASA on this NASA flagship mission. And that opens the way to for the L5 theme to be a successor of our Gaia mission, but with detectors which are not in the optical, but in the infrared. So when you actually, like James Webb, can then look through the clouds of gas and dust, and you can find many more stars with such an infrared mission. Now, just a few months ago, the Decadal Survey for Planetary Sciences came out. And apart from the stating that the Mars sample return mission and the Mars missions and the Jupiter missions, the Europa Clipper and so on, are continuing to be high priority. The two new priorities that came out of the Decadal Survey were a Uranus mission going to our ice giant planet Uranus that has never been visited before, and an Enceladus orbilander, so something that is orbiting and hopefully landing on Enceladus. And so it turns out that the second priority of NASA is more or less commensurable with the first priority of ESA. And so it's very possible that we could cooperate on such an exciting flagship mission. And then on the other hand, we would, similar to what we will do for the exoplanet mission, we will also hope to collaborate on the Uranus mission in a similar way as we have done with Cassini-Huygens, where we have provided the landing probe on Huygens. I think this time we could, for instance, ESA could provide an atmospheric probe that dives into the atmosphere of Uranus, while NASA provides the orbiter. So these are the possible attachment points and the skeleton, or sort of the next steps for working together on a grand scheme. And so down here, what is shown is basically one possible incarnation that has to be discussed now within the ESA member states. It has to be discussed with NASA, but it provides a very good scaffolding, so to speak, of the future. So our L4 mission could be an ESA-led Enceladus mission with a strong NASA participation. Our L5 mission would then be the ESA-only Gaia near-infrared mission. And then we would think about an ESA contribution to a Uranus mission and an ESA contribution to an astrophysics, and then also maybe later the heliophysics flagship missions, because heliophysics is still working. They have not yet started their decadal survey, but The general message is that we would like to cooperate on most or all of the NASA flagship missions, and we would hope that NASA is also cooperating as a smaller partner on our flagship missions. And so this is a very good way of working together. And we have already started the first steps. We have created a team of European scientists, a topical or an expert team that will actually look to, that has already started to look at how the first L4 mission can look like. So the large mission of Voyage 2050. And they also look at much more ambitious mission profiles, including a lander and a return element, which could pave to the way to an Inspirator mission, which is significantly larger than a typical ESA science mission, namely the Icy Moon Sample Return Inspirator mission. And with this, I would like to stop, and I'm very happy to take some questions and discuss with you more. Thank you very much for your attention. So Terry, I am seeing these questions. Do you still hear me? You are muted, I believe. Oh. Yeah, no, you are muted.
There we go.
Yeah, okay, now got you.
Okay. Anyone who wants to ask a question, you can go to the Q&A section down at the bottom of your screen and put in your question there. The first question is, please explain a bit more about why the L2 region is special for parking missions.
Yes. So there are actually there are a total of 5 so-called Lagrange points. The scientist, the mathematician Lagrange has identified those points, and this is where the gravity of 2 bodies is actually canceling out. So you could imagine if you, for instance, have the sun and the Earth, then somewhere in between the sun and the Earth, the gravitational pull of the sun is the same as the one on the Earth. And so if you park a satellite there, then it is kind of stable. It's not exactly stable because it can always be pulled in one direction or another. And you also have to take into account that the sun and the Earth are moving. So it is not just the sheer gravity, but it's also the centrifugal force that is playing a role. So if you add up all of this, then you are getting 5 Lagrange points. Lagrange point L1 is actually exactly between the sun and the Earth. And the Lagrange point L2 is exactly on the opposite side. So it is behind the Earth as viewed from the sun. And L2 is actually, and then there is an L4 and an L5, which are on opposite sides to the left and to the right of the axis Sun Earth. The Lagrange point 2 is special because it is basically, it always has the sun and the Earth in the same side of the spacecraft. And so like on Gaia or on James Webb, if you have a solar array or if you have a solar shield, then both the Earth and the sun basically can be shielded at the same time, and while the telescope is looking in the cold sky. And therefore it's a very special place where you can park. It's not really parking, you know, that they have to move these Lissajous figures so that otherwise they would fly away. But it is with minimum energy, you can actually stay there for a long time.
Can you say a bit more about the hypothesis that dark matter is produced by primordial black holes?
Yes, I can do that. You know that physicists were looking for a long time for dark matter, and there were many different theories about particles, different types of particles, so-called WIMPs, axions, supersymmetric particles, heavy neutrinos, and all of these. And so for many decades, physicists have tried to measure these particles in Earth experiments, in accelerators and in other experiments, and they haven't found anything. And I think a lot of the theories are now basically coming to areas where it's really hard to hide a particle. However, the black holes have actually never fully been ruled out. Stephen Hawking, when he discovered or actually calculated that black holes can radiate the so-called Hawking radiation. He predicted that black holes could evaporate. So a black hole, when you wait long enough, could get smaller, 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 and smaller, and in the end, it would explode in a gamma ray flash. And so for a while, Steve Hawkins was speculating whether the dark matter could be made out of these little black holes which would evaporate. And that theory then has been put to rest because these black holes would create a gamma ray background which was not seen. But what Stephen Hawking did not look at is black holes which are so big that they can survive for much longer than the lifetime of the universe. So if you are looking at a black hole of stellar mass or maybe even a supermassive black hole, they can live for such a long time that they would not evaporate. And indeed, now people start to believe again, and I'm a strong believer of that the primordial black holes, which are created right after the Big Bang, in the first 2 seconds after the Big Bang, could actually be the solution to a lot of mysteries that we have found, which we cannot explain otherwise.
Can you speak more about the Plato project? Where will it be positioned, and will they image at different wavelengths? Why 26 telescopes?
Okay, yeah. So Plato will also be positioned at the L2 point, so it will become quite crowded there, and it will, similar to Kepler and TESS, will basically look at a region in the sky where there are many stars, and then it looks at 1 million stars at the same time, and then it looks for instance, these transits. So when a piece of the light is missing because a planet is moving in front of the star. Now, Kepler had one telescope and was looking at a particular region in the Cygnus part of the sky. And the planets there that they discovered were typically relatively far away, like about 1,500 light years or more. And Plato is now looking at closer by planets. And so they cannot just look at one part of the sky, they have to look at a very large fraction of the sky. And so instead of doing that through one telescope, they have actually 26 telescopes, and each of them looks in a slightly different direction so they can cover a large solid angle. And that way, because you need to look at millions of stars to find these few thousand exoplanets, and Plato will be able to look at, in particular, the bright nearby stars, all of them at the same time.
What are the prospects of breakthroughs in space travel to make it fast enough to more efficiently and quickly explore, especially the solar system and the planets and moons of the giants?
Yes, I mean, so you know that Voyager is on its way since more than 40 years, and it has just made it out of the solar system. Then there was the New Horizons probe, which was already going twice as fast as Voyager, and it's almost there where Voyager is now. And indeed, NASA is thinking about an interstellar probe that is going even faster and going out of the solar system. At some point, physics is your boundary, so you cannot produce very much more powerful machines. So I believe, and then at some point, I believe that Einstein's velocity of light is just the limit that you can think about. So even if you would try to accelerate something to maybe half of the speed of light or so, you would already need so much energy that this could basically more or less evaporate the whole energy budget of the Earth or something like that. So I believe the only way to do that is to go reasonably fast, but still slow. And then you would probably either have to send whole generations of people who could renew in orbit. So send us a space station where you then get children and kids of children, and your grandmother is then arriving at your destination. Or another possibility would be maybe to cryogenically freeze the people and then thaw them up again after 100 or 200 years before you go there. So I'm a fan of science fiction, but I don't really believe that this warp drives and things like that can work.
Well, with that, I think we're out of time. I want to thank you so much, Doctor. Thank Donna McCormick, our director, and East Hampton Library folks for putting this together. Anyone have a last question? If not, we'll.
Terry, Matthew has raised his hand, so maybe he wants to speak. Can we let him speak?
Yes, of course.
Matthew, but I think you need to be unmuted by maybe Donna or yeah, here's Matthew.
Okay, there we go.
Matthew, can you talk? Oh, Matthew, can you talk? Looks like not. And maybe you have to put your question into the Q&A. I think we have Lydia sent wonderful presentation. Thank you. And there are two other participants.
There's no Donna's.
Matthew, talking is permitted. No, so we don't get anything.
There's Matthew. The Russians are looking at atomic fusion generated rocket fuel. Is the ESA looking at similar fuels?
You know that I worked for quite a while in nuclear fusion for the ground-based, I mean, to solve our energy problem on the ground. And I still believe that in about, I don't know, at the end of the century or so, we may have nuclear fusion working. From all the studies that I have seen, you need a very large reactor to be able to maintain the heat in the. This is basically similar to when you are looking at a mouse and compare it to an elephant. The mouse, the ratio of the surface of the mouse to the volume of the mouse is much worse than for the elephant. So you need actually, and you are losing energy through the surface of your ball. So you need very, very big plasma fusion devices to work. And so I just don't believe that you can have small fusion devices. And whoever is looking at them, I believe they are, again, science fiction, for the moment at least.
Well, with that, I think we're good. Thank you, Doctor, so much, and good luck in the next mission.
Thank you very much. It was a great pleasure, and have a nice day. Nice rest.
Thank you so much, everyone. Thank you, Terry. Thank you, Doctor. Thank you, everyone. Have a great day.
Bye.
Bye-bye.
Bye.